Dave, are you good?
Yes, sir. Can you hear me okay?
We can hear you, you can hear us, but it's perfect. So we can start the presentation.
Excellent.
I'll try to give you a view in the room a bit, like this.
Okay, great. Let me ask you, if I do this, is my presentation still full screen?
No.
Okay, I'll go ahead and make it full screen. That means I won't be able to see the room. Please holler at me if there's any questions or anything.
Yeah, we'll do that.
Okay, great. All right.
Yeah, good to go.
Okay, hi everybody. Glad to be talking to you today about Singularity. So, I don't know if Kent has already introduced me. My name's Dave Godlove. I'm a software engineer working at Sylabs, which is the new company that Greg Kurtzer just founded to work with Singularity. My background is that I used to be a scientist working at the National Institutes of Mental Health, and I was analyzing my data on the High Performance Computing Center resource called BioWolf there, and so I became interested in HPC. And I decided to make a little bit of a career shift and become a computational biologist. While I was there working at NIH HPC, I learned of Greg and his work and of Singularity, and I ultimately, became so enamored with Singularity and really liked the community so much that I decided to leave the NIH and become a software engineer working at Sylabs. So that's who I am and the angle that I'll be talking to you today about Singularity from. Greg needs no introduction. He is the inventor and the lead developer of Singularity. He's also the CEO of Sylabs. This is the new company that he's just founded to develop and provide support for Singularity. He's also the senior architect at RStore, which is our parent company. Previously, he was a systems architect at Lawrence Berkeley National Labs. He was there for around 20 years. And he's been in the open source community for quite some time, too. So he's led high-profile projects like Werewolf, which is a provisioning tool for HPC, which is really widely used. He also founded CentOS. So if you're familiar with or use CentOS Linux, you have him to thank for that. And obviously, he's also the project lead for Singularity, which I just mentioned. I bring up those things not only to introduce Greg, but also to let you know that Greg's got a lot of experience in the open source community, and also that he is really an HPC person. So Singularity was built by HPC people for HPC people, and that's something I'm really going to be stressing throughout this talk. I also have quotes sprinkled throughout the talk, like this one from an admin at the Institut Pasteur. So he says that Singularity plus Werewolf plus CentOS is a winning combo. So this is he's really talking about Greg's work here and how they use all three of those products there at their institute. Okay, so just to begin with today, I think I'm going to give a really short level set and just talk about what a container is. And then I'm going to talk about how Singularity is different from the other container solutions which are available today. Okay, so just Containers 101. Let's pretend that this Singularity logo is our container here. So what is a container? Well, a container is an encapsulation of an operating system. At a very high level, that's what a container is. So if you want to build a container, the first thing you'll do is decide, what kind of operating system you want to install within the container. And after that, you'll decide what sorts of applications and what sorts of dependencies and libraries and so on you want to install in your container. So let's say you've got a workflow which, I don't know why you'd have this, but for whatever reason has all these applications that are all needed to make it run. You would go ahead and install all of those with all the dependencies inside your application or inside your container. And then your container is going to include all of the dependencies right down to the glibc and even the operating system itself. This is going to give you the workflow which is completely self-contained and portable. So now if you want to, take that container, to an HPC system, or you want to take it up to the cloud, or you want to send it to a colleague. It's really easy to do that. With Singularity, actually, it's extremely easy to move these containers around because each one is just a single file. I'm going to be talking more about that throughout the talk. In the container landscape, there are multiple implementations that exist. Singularity is just one of those. So containers have been around for some time. The Singularity, it's different than other container solutions for several reasons. One of those is its architecture, and another one is the container format. And I'll be going into more details about those things throughout the remainder of this talk. So if you want to understand what a container is, I think it's useful to think about what it's not, and kind of compare and contrast it with a virtual machine. So what I just described, if you're not familiar with containers, might sound an awful lot like a virtual machine. So let's think about that for a second. Let's consider first a case in which you're running an application on bare metal and think about what that looks like. So if you're running on bare metal, you've got just some hardware. On top of that hardware, you've got a host kernel and you've got a file system, and then your applications, your bare metal applications just run natively right on top of that file system. If you're running a virtual machine, the first thing you need to do is virtualize that hardware, and then you're probably going to have some optimizations between your virtualized hardware and the physical hardware to try to drive that virtualized hardware as quickly and as optimally as possible. Then you're going to have another kernel and another file system which sits on top of the virtualized hardware, and finally your applications are going to run on top of that. So this is basically what the full stack from the physical hardware up to the applications looks like in a virtual machine. If we contrast that with the container architecture, once again, we have the physical hardware, the host kernel, the file system, and the native applications running, but the container sits right at this level. So essentially we're pushing the file system out of the way, and we're putting a new file system in. And then your applications just run right on top of that other file system. You share the host kernel, and so really the take-home message from this slide is that the distance here, A, is less than B, and that's because of C. Virtual machines have been really optimized, and depending on what applications you're running, they may run very quickly in a virtual machine. Depending on what applications you're running too, they might not run as quickly. But really, if you're running a containerized application, it's going to run pretty much the same as a native application. And I'm even going to show you some examples later on in the talk in which the containerized applications run faster than native. So I mentioned that there are lots of different container platforms out there. So what makes Singularity stand out? What makes it different among the container solutions which currently exist? Let's talk about its unique features. First off, as I've alluded to, Singularity was built specifically to support high-performance computing and science. So Greg invented and developed Singularity when he was the HPC architect at Lawrence Berkeley. And he did so in response to the needs of the users. So they came to him and said, we really need to run containers. He looked at the container landscape and realized that there was a mismatch between the current container solutions which existed and HPC, and he really created Singularity from the ground up to fit that, to fit in the gap there. Singularity has a single file-based container format. I already kind of alluded to that as well. That's really different from any other container solution that I know of that currently exists, and it seems like really kind of a dead bang simple, almost stupid kind of thing. We've got a single file container format, but that one little trivial detail actually opens up a lot of things for us, a lot of areas that we can develop. So for instance, this makes our containers extremely movable. So Singularity containers, just using SCP, rsync, whatever tools you're already using, you can move them from one place to another. It also means that your containers are controls compliant. So, maybe you're working with personally identifiable information like social security numbers or medical records. Or maybe you've got data which is which is classified and you need a security clearance or something. If you've got controls on your system which are in place to protect your data, those same controls are also going to protect your containers because they're just data, just like any other data. So another thing that sets Singularity apart is that we're compatible with complicated architectures like HPC, machine learning, etc. And I'll be going through some of those details later on. And finally, Singularity has a unique security model. In a nutshell, most container solutions essentially assume that there are only going to be trusted users running trusted containers. And what I mean by that is users who either already have root privileges or it'll be okay for them to have root privileges running containers that, don't have malicious code inside of them. In the Singularity model, it's fine to have users who you don't trust, who are not allowed to have root privileges, running containers that haven't been vetted and may actually have malicious code inside of them. That's actually what we expect that we're going to be running in Singularity. Okay, so those are the things that make Singularity unique. Now I want to get into a little bit more detail about the Singularity image format, SIF. So as I've said a few times now, Singularity containers are just single images or single files. What do those files look like? If you've been using Singularity in the past, you'll probably remember that we used to support ext3 or squashfs images as our files. We've moved away from that now in the development branch, and now we've got our own file format. It's kind of similar to an ELF file format. It's a global header, and it's got some object descriptors. Those object descriptors are going to point to data objects within the file. Okay, so that's what the layout looks like. And so to get a little bit more detail, what we'll have is in SIF is this global header, and then we'll have descriptors, and then the data objects are going to be things like the definition files, so metadata, labels, the environment that the container is going to run in. And then we still have, as one of these data objects, the actual file system. In this case, we're continuing to use the squashfs compressed file system, which runs compressed, and that's going to be immutable as well, so you're not going to be able to write to that file system on default. What this allows us to do, one of the many things this allows us to do, is to have another data object here, perhaps a signature block, that allows us to cryptographically sign all the other data objects that exist within the container. So with the SIF file format, what we now have is the ability to have self-signed containers that you can pass from one environment to another, that you could receive from a colleague or send to a colleague, and then you can verify that that container hasn't been changed and has within it what you expect it to have inside of it. Another thing that the SIF format allows us to do is, in addition to the signature block, we can also put other data objects in. For instance, maybe we will put a writable overlay. This is something we're actively working on right now. This is something which is coming down the road. What that's going to allow us to do is, not only do you have a cryptographically signed container where all those signatures apply to all these immutable data objects within the container, but in addition, you also have an unsigned writable portion of the container which can evolve over time. So I'm going to give you a couple of potential use cases for this that we're thinking about. One idea is maybe you can checkpoint your containers and pause them while they're running, and then move them from one environment to another and then restart them. So that maybe this writable overlay can hold on to the state of the container so that you don't have to move any additional data with the container. It basically knows where it paused and knows how to restart itself in the new environment. Or maybe you're working with artificial intelligence and deep learning and things like that, and so you've got some sort of machine learning a program or a framework which is installed in the immutable portion of the container, but then you've got a model and some data in the writable overlay. So you move your container up to HPC, you train your model, set your weights, and then you can move the same container down to your personal system, which doesn't have all the horsepower to train, but which does have now enough horsepower to do like classification with the trained model. So these are just a few of the things that we're thinking about with this new container format. Okay, so the features that we currently have are we're working on in SIF. Once again, cryptographic signatures and verification, either for the entire image or for regions within the image. SIF is going to have faster access to the metadata. This is because the metadata no longer resides in the file system as it did previously with older versions of Singularity. Now it's actually outside of the file system. As I said before, we're going to support multiple system partitions. And ultimately, we're looking at things like supporting checkpoint and restart using this file format. Okay, so that's what the single file container looks like within Singularity. Now let's talk a little bit about reproducibility and portability, some of the advantages that you get with the single file system. Greg likes to show this metaphor. So with the currently used container solutions which exist out there right now, if you need to recreate a container with the existing infrastructure which currently is there and the existing methods, the way that most people do it is to just rebuild the container from the ground up. So this means re-downloading a series of layers or moving a series of layers from one place to another, splatting them all out, creating a presentation layer based on that. So that's sort of metaphorically similar to, if you want to reproduce this Van Gogh, painting it from the ground up. If any of your layers have changed or any of your data has changed or anything about your runtime or the way that you create the presentation layer has changed, then your container is going to be similar to the one you had previously, but it might not be identical. With Singularity, you don't have to worry about that. So this emphasis on reproducibility is one of the reasons why the scientific community has really jumped on Singularity and has really become excited about Singularity. So once again, with a single image, you can just copy it, and then, if you took like a SHA-SUM of the original container and its copy, you would see that they're identical. So Singularity ensures bit-for-bit software reproducibility. At the University of Michigan, they've noticed this, and they've commented that Singularity is a great tool for providing forward and backward compatibility and also for reproducibility. So this is being noticed by people in the community. And once again, just to re-articulate this, this is just an added benefit that we get from having this single file container. You can just move it around using whatever existing tools you've got to move data from one place to another, and then you can take your containers up to the cloud, run them there, or you can run them on HPC resources like the Open Science Grid, which currently runs Singularity, Penguin Computing, for instance, which is one of our big advocates, and Xseed. Not all the Xseed clusters currently run in Singularity, but quite a few of them do. Okay, so now I've alluded to a few times how Singularity is really built for HPC, and I'm also going to introduce this new term, EPC. I want to get a little bit more into the nitty-gritty details of why that's so. Okay, so what is EPC? First, let's talk about what is HPC. So I think that this crowd is probably well aware of the features that sort of define HPC. If you're talking about HPC, you're talking about low latency, high throughput networking, like InfiniBand or OmniPath, for instance, big parallel file systems like Lustre, GPFS, BGFS, things like that. In many cases, not all cases, but in many cases, you're talking about MPI. You're talking about resource managers like Slurm, PBS, Torque, etc., and running your jobs through those. And increasingly, but not exclusively, we're also talking about GPUs. So massively parallel computations, right within a single node. We're seeing kind of a shift in the enterprise where a lot of enterprise users are becoming more interested in technologies like artificial intelligence, deep learning, computer-driven analytics, IoT, things of that nature. And those users are starting to demand HPC-like resources. So, whereas previously these users might use systems that are not very HPC-like, now they're starting to gravitate more towards HPC-like systems. So this new enterprise performance computing area is also a place where Singularity is really, it's in a unique position to really provide the container solution. Why is that? One of the things that I alluded to is that we have a unique security model. So recall that I said that Singularity is set up to allow untrusted users to run untrusted containers. This is important on multi-tenant systems where you've got lots of users logging into the same system and the administrators don't necessarily trust them. How do we do that? We do that by limiting the user's potential security context. So whatever user you are, whatever UID you have, when you enter the container, that's the UID that you have within the container. You're not allowed to escalate your privileges to root, and that's even if you install sudo inside the container, or even if you set root's password and you know it, or even in some cases, if you have kernel level exploits installed within the container. So Singularity is actually able to block some types of exploits. So we also allow users to access data they own, and we also limit access to data that they don't own. So since you're the same user inside the Singularity container, you can write data out to the host system, and that data is going to be owned by you with the same UID, and it's going to have the correct permissions and everything. And it's going to be set up perfectly, just as if you wrote that data from outside of the container. This has led a lot of admins to install Singularity on HPC resources where they wouldn't install other types of container solutions. So in Washington University of St. Louis, for instance, one of the admins said, basically, the users have been asking for containers for a long time, and they wouldn't comply with installing a container solution until Singularity came out. So that's security. What are some of the other things that make Singularity a good fit for HPC and for EPC? Well, Singularity natively supports MPI. So, and it leverages actually the MPI which is installed on the host system. It does so using a hybrid model. I can talk a little bit more about that in detail later if you'd like. Singularity also leverages the GPU, and it does so natively and transparently. So if you want to use the underlying GPU hardware with Singularity, all you have to do is patch the --NV option, and Singularity is going to locate NVIDIA libraries and binaries on the host system and map them directly into the container for you. We're also compatible with the resource manager. So I'll get into that a little bit more in detail later, but Singularity doesn't use like a root of a daemon to launch jobs. It basically just launches jobs or launches processes just like any other processes running on the system. So resource managers can manage Singularity jobs with ease. I already commented that we've got a single file container format. And in this context, it's important to realize that this container format is highly optimized for parallel file systems. So having a single file container can actually help with the speed of a parallel file system. And I'll talk about that a little bit later if I have time as well. The Department of Defense uses Singularity, so the Army Research Lab uses Singularity, and Madden there says that Singularity is the best option among the big three considerations for HPC. I mentioned just a few slides ago that Singularity is compatible with resource managers, right? So how does that work? Well, let's say you're using another container solution. If you're trying to submit a job, say through Slurm, and you're using some other container solution, usually you're going to have to interact with a root daemon. So you submit your job, your batch script, or your commands to start your shell, and then that passes off control to a root daemon. The root daemon and the resource manager can talk to one another, and then the daemon actually executes your programs on your behalf. outside of the purview of the HPC or the resource manager here. So that's kind of a problem, because now the HPC resource manager's got no idea what's running on its nodes, doesn't really have control over those processes. But with Singularity, essentially Singularity starts up and spawns your programs and then just executes itself back out of existence, so that your programs are running within the same PID context, UID context, and with all the same user privileges as any other programs that would run on the system. The resource manager can see them and can, manage them as it ought to. We'll talk a little bit about performance. So here is an instance in which we're running NPI, and we're either running it natively here on a CentOS 7.2 system, or we're running it within a Singularity container, running either CentOS 7.3 or Ubuntu 16.04. And you can see the latency and the bandwidth is actually less for the containerized MPI. Now, this is a little bit of a contrived example. Obviously, we're running a little bit of a later operating system within the container, but this shows you that you can leverage things like a later glibc within the container, and this can give you actually some performance boosts. It can also allow you to install programs that you would otherwise be unable to install. So at Rutgers, this is one of the main use cases for Singularity, to install a glibc, which is compatible with other programs that they'd like to install. This is also a major use case at the University of Chicago. Things like TensorFlow that you can't install under RHEL 6, with Singularity you can't install.
10 minutes.
Got it, okay. I'll try to wrap up quickly. Okay, so let's see. I mentioned earlier that the single file container format can actually give you some boosts in performance on a parallel file system. So just really briefly, one of my ex-colleagues, or one of my colleagues at the National Institute of Health, did this experiment during a downtime where he ran a lot of parallel instances of Python, and he either ran them just on bare metal, installed in the Conda environment, or he ran them here in the containerized environment. And he actually found that the containerized environment ran a lot faster. So I'd like to point out this is a log-log scale, so this is actually a very big difference. And the reason for this is because Singularity allows for the handling of metadata lookups. It allows for that to basically just have fewer metadata lookups. And it also, when you run a Singularity container, usually that container is mounted as read-only, which allows for the kernel to do things like efficient caching and things. And so that makes things run quite a bit faster. And that's another performance benefit that we get just out of having a single file container format. Okay, I'm going to go through this really quickly so we can wrap up. There are a lot of different institutes and organizations which are using Singularity. For instance, Nextflow, which is used by a lot of genomics pipelines, is using Singularity. Nextflow is run at these institutes. I'm just going to go through this really quickly. The University of Cape Town has got kind of an interesting use case for Singularity. So they're using GitHub kernels. They're deploying those within Singularity containers and then allowing users to interact with those containers, interact with those different kernels. Let's see, the Green Cube at GSI. They are running at any given time about 2,000 Singularity containers on their system. The Open Science Grid, at the time that this slide was created, which is actually some time ago now, they're running about 500,000 jobs per day using Singularity. That's now, I understand, up to about 1 million jobs per day. Oak Ridge is running Singularity, so Titan, the biggest Cray supercomputer in the world, is running Singularity. And obviously NIH, I've talked about NIH a few times because that's where I came from. One of the interesting things we did at NIH is to install applications for users within Singularity containers and then write wrapper scripts so that the users would think that those applications were installed just natively on the system. They didn't even realize they were using containers when they were running the applications. I'd like to tell you a little bit about our roadmap. So here are some of the things that we're looking at that we're actively, excuse me, we're actively trying to develop. One of the things that we'd like to do is have containers that you can actually boot within instances. So this is going to allow you to basically run a container like it's a virtual machine. I already told you about the well-assigned containers. We're going to change the privileges in Singularity a little bit so that we remove the SUID bits and we use Linux capabilities instead to allow more fine-grained control of privilege contexts. We are developing currently, we're really working towards getting Singularity OCI compliant. And so what that means is we're going to have native Kubernetes support, and we're going to have support for all the different container tools that exist out there, which can plug into an OCI compliant container. Checkpointing and restarting, I already mentioned. We're looking at performance profiling. So let's say you install an application inside a container, and then you've got a native tool in Singularity to profile the I/O, CPU usage, the memory in that container. And finally, we're looking at supporting Singularity also on MSX and on Windows. Here are some of the people and some of the institutions and centers and so on that have contributed to Singularity. So I want to say thank you very much to all these places. And thanks a lot for your time. And if you want to learn more about Singularity, here are some of the places that you can go to. Good, so thanks a lot.
Thank you very much, Dave. Any questions? Yeah.
Do you have any ETA about checkpointing implementation?
Is there an ETA on checkpointing support?
No. Unfortunately, we don't have an ETA on that right now. That's actually, I don't think, so we have a roadmap for things that we're trying to include in the 3.0 release, which should be coming out around summer. That's one of the things that we're working on, but we don't have it slated for the 3.0 release. So it's probably going to be further out in the summer.
Okay.
Do you have an idea of how you're going to do that? Is that going to be something dedicated in Singularity, or are you looking at the MTCP, or?
We're going to be looking at the, that's not something I'm working on, but we are going to be using existing tools, which are already out there. I think that the trouble is that the existing tools that are already out there, they might need a little bit of development themselves for us to be able to use them, so that they're not perfect. But yeah, we're not going to be developing anything from scratch.
One thing that has come up a couple of times here throughout the week is that the way you usually build containers is in a generically optimized way. So, for example, SSE2, so you're sure you can run it in a lot of different places, and that it just works. In some sense, then you're trading off portability for performance.
Yes.
Is that something you're worried about, or do you think portability is more important than performance, or?
Yeah. So let me talk about that a little bit. So one of the things that we've tried to do is not make that trade-off. We're trying to have both portability and performance. And I can use as an example, for instance, the way that we implement the --NV option, the way that we're able to use the NVIDIA hardware as an example. So it used to be, and it still is with most container solutions, that if you want performance, you're going to be, just as you said, trading portability, because you've got to install directly within the container all the specific drivers that you're going to use on the specific system that you're going to use them. And that's going to give you great performance, but it's also going to mean that you can't run your container anywhere else. So that's one of the things that we do with Singularity. We blur the lines between the host system and the container. We're actually not so interested in isolating the container from the host system. And so this allows us to do things like leverage the underlying software where applicable, the underlying drivers and things, to make sure that our performance is as fast as it can possibly be. But to make those containers, portable, where if you move them from one host to another, they're still able to leverage whatever, software and whatever hardware exists on that different host.
Right, and are they also looking at building, or maybe better dedicated support, or maybe just a matter of documentation, having fat containers in the sense that they can both support AVX, AVX2, these advanced capabilities of processors, and then whenever they are not there, you just fall back to whatever is supported? Is that something that people are doing, or?
Yeah, so that. I know of a few homegrown implementations, so you can build your container to do that. One of the things that you can do right now is you can leverage our existing SciF capabilities to be able to do that. So Vanessa Socat has worked on this whole kind of like branch of how you build containers with SciF, which means you take multiple applications and you install them all within the same container. So what you can do is you can install multiple, you can compile basically your application from multiple different architectures, install all those within the same container, and then at runtime, you can query the architecture and load whichever version of it you need. That's a little bit cumbersome. I don't really know how we would just make that, transparent and trivial to the user. Right now, it's kind of on the user to be able to do that themselves.
Yeah. I think the answer there may be Singularity, maybe EasyBuild. EasyBuild knows how to build stuff from source, and it can spit out Singularity images. Or
right.
So that's something we can take a look at. We've discussed the integration before. Things haven't moved a lot there, but Shazette has been working on the integration a bit. That's maybe something you and me and Greg and Shazette should get back to.
Yeah, definitely. Yeah. Well, actually, one of the implementations I'm aware of did use EasyBuild within the container to install LMOD, and then to load whatever environment was needed based on the architecture with the LMOD of the container.
All right, cool. Any other questions?
I'm still more interested in the support of Singularity on MPI.
Yeah. So the one question that came up today is that how Singularity exactly supports MPI, because there has to be some amount of compatibility between the host MPI and the MPI in the container. Can you say something about that?
Yes, I can say a little bit about it, but I can't. So Greg is actually the expert on that, but I can speak to it to some extent. So it turns out that there is a great deal of compatibility between a lot of different implementations of MPI installed within the container and installed outside of the container. I don't know all the details, but I think that MPI uses some plugins, which might be common between multiple different implementations, which allow for that compatibility. So while it is the case that you probably want to try to figure out, what environment you can run your container in, and you want to try to match as closely as you can the MPI within the container to the host system. It turns out in practice that isn't always necessary. There are a lot of different MPI implementations that will work with one another, so you can actually be a little bit looser in your matching, I guess, and things will still work. I don't know all the details about that, but I will tell you that we have a lot of MPI experts within our community, and so if you're interested in that, contact me or contact another one of the Sylabs members, and we can give you an invitation to our Slack. And there's almost 300 people in Slack right now, and a lot of them are MPI experts, and a lot of them can give you tons of information about what will work and what will not work.
All right. Is this well covered in the documentation as well?
I think actually I've got an open PR or an open issue in our documentation repo that we need an MPI expert to do a write-up. So I don't think it's currently well.
Okay. We'll pass the message and ask more information through Slack. All right. Thank you very much.
Thank you.